Hello everyone. This is an example that accompanies lecture 14 on kinematics and velocity fields. And today we'll be talking about some mathematical functions and doing some examples of some calculations of different kinematic quantities for these velocity fields. So first I'm just going to remind us the different things that we care about. Oh, where did my we care about translation, we care about rotation, and we care about deformation of different material elements in our velocity field. And we had mathematical quantities that I said we could calculate for these. So for translation, we have stream functions and streamlines. So I'll put streamlines here. For rotation, we have vorticity. And then for deformation, we have the shear rate. Alright, and these two are what we're going to calculate today. This one we're not, because the shear rate we're going to see we will need a tensor to do, so we're not going to do that today, but this we will do today. Alright, so the example I've chosen is one of simple shear flow. This is a flow field that we've encountered already several times in the course, and we'll see several more. In this case I have two parallel plates, a bottom plate and an upper plate. The bottom plate I'm calling at y equals 0, and the upper plate I have at y equals h, following this gap of h. And the upper plate moves at a velocity u. And what that does is it drags fluid along with it, and the fluid right at the top is moving u at velocity u, and at the bottom I'm sort of stuck to the bottom plate and I'm moving at a velocity of 0. And so the flow field here, which I haven't derived rigorously, but I'm telling you that this is the solution, and we will derive this later in the course, is I have an x component of the velocity, so that's in this direction, that is u y over h, and there is no y component of the velocity. So that means there's no velocity down or up, there's only velocity side to side. But the x component varies with the y direction, which is what I just told you. So at the bottom, when y equals 0, I get a 0 here. So the velocity in the x direction is 0. And when I'm at the top, y equals h cancels and I get a velocity of u. And then I have a linear equation, so it varies linearly in between. Alright, so what we'd like to do is look at the stream functions and the vorticity of this system. So we'd like to know how is translation and how is rotation happening. So the first piece I'll put down here, let me reorient my guy a little bit. So let me put A right here, and I'm going to say what are the streamlines? Okay, and well, I'm going to undo that guy. That was a terrible line. Let me draw a little bit better line for you there. Okay, so what are the streamlines? So recall that to calculate the streamlines I need to calculate a stream function, and so I have this relationship for the stream function that says that the x component of the velocity is equal to d psi dy, where psi is my stream function. So I'm going to have psi is the stream function. And I'm going to have the y component is equal to minus d psi dx. Right, and this is a definition of the stream function, and what I'm going to do now is, in order to calculate the streamlines, I need to know what the stream function is. So let's calculate the stream function. Well, calculating the stream function is sort of like recovering a function from a gradient. It's not exactly a gradient because I have this minus sign here, but the mathematical process is the same, or very similar. So let me start. I know what d psi dy is. That's equal to vx, which is this function I have right up here, u y divided by h. Now what I want to do is I want to get psi, so I'm going to take the integral of both sides with respect to dy. So taking that integral, I get that psi is equal to uy squared divided by 2h plus a constant. So this constant, as far as I know, could depend on x because I only integrated with respect to y, and I know that psi depends on both y and x. So now I need to check using my other part, my derivative with respect to x, whether or not this constant depends on x or not. So now I'm going to come over here and I'm going to say d psi dx. Well, I'm going to use this thing first, this function I just cited. So this does not depend on x, but that one might. So I'm going to write dc1 dx. And I know that d psi dx is going to equal minus vy. Well, vy is 0, so it doesn't matter if I take the negative of it. So I get a 0. So now I'm saying that dc1 dx equals 0. And I can integrate this expression. And if I integrate that, I just get that c1 is just a constant. Okay, so I proved that this doesn't depend on x. So now I can write my total stream function as 1/2 uy squared divided by h plus c1, where c1 now is truly a constant. Okay, so now what I told you is that we need to find streamlines. So what are streamlines? Well, I said that lines of constant stream function are streamlines. So I can rearrange this to find what my y values are for my streamlines. So I'm going to find an equation that describes my streamlines when I set psi equal to a constant. So I'm going to say this is equal to another constant. Let me call it c2. So now I have 1/2 uy squared divided by h plus c1 equals c2. Well, I can subtract c1 from both sides, which cancels this one out, which I can just erase. All right, and now I look at this and I say I can multiply by 2h, so I have and divide by u, so I have y squared is equal to c2 minus c1 multiplied by 2h divided by u. And now to find y finally, I will say y is equal to the 1/2 power of 2h. And I'm going to call this c2 minus c1. That's just some other constant. I don't even care what it is. I get to pick it. 2h divided by c3 over u to the 1/2. Okay, so what is this telling me? This says that y equals, and then h is a constant, u is a constant, and c3 is a constant I get to pick. So y is just equal to some number. So there's no x values here. So this tells me that my streamlines are just constants. Oops. So I'm going to draw here coordinate system if I can manage it to be straight enough. And what this is telling me is that, if this is x and this is the y direction here, that if I pick a value of c, which I can vary, I'm going to get a line. And then if I pick a different value of c, I'm going to get another line. And I'm going to get another line. And so my streamlines are just straight lines. Right? And that makes a lot of sense. That's what I drew up here. They're just straight lines. Okay? So no x dependence. Okay? So that's the first part, is how to calculate streamlines. So my translation, if I have a material element and it's sitting in the flow here, it just translates to the right. Just translates to the right. Okay. Part B, now I'm going to ask, what is the vorticity? Okay, or I'm asking about rotation. Okay, now recall that the vorticity is defined as the curl of the velocity. Well, in 2 dimensions, which is what this flow is, I can write that as follows. Now I got to look at my little sheet of paper here. So the vorticity, and this, by the way, you can look in your book. This is table 5.3 in Dean. All right. So in this case, if you don't want to remember what how to do the cross product, dvz dy minus dvy dz, and that's in the x direction, ex, plus, oh, my hand's kind of hurting trying to do this, getting over here to the edge, dvx dz minus dvz dx, and that's in the EY direction. Oh, and I think I should have had, shouldn't there be a minus sign on that somewhere? Maybe, let me look in the book and make sure I didn't screw that up. I thought there was a minus sign. Nope, that looks okay. Sorry for that. Alright, the last one is dvy dz minus dvz dy. This is wrong. dvy dx, not dz. dx and dvx dy. dvx dy. And that's in the EZ direction. Okay, so this is now what I need to calculate to find the vorticity. Well, I look at this and I say I have no VZs, so I can just ignore these VZs. That's 0. I have dvy, that's also 0, so 0, and there's a VZ, that's 0, and there's a Vy, that's 0. So all those that I crossed out are 0. So now I look and I say dvx dz, well, Vx only depends on y, so that's also 0, so 0, 0, 0, 0, 0, all the way across. The only one I have is this one, minus dvx dy. So now I need to calculate dy of, and now Vx is uy divided by h, and that's in the z direction. So the derivative with that respect to y is minus u divided by h ez. So what is this telling me? So that's my vorticity, by the way. That's the final answer. I should have maybe boxed that one too. Those are my streamlines. Okay. And there's my stream function. Should have boxed that one. This is telling me that I have rotation, and what direction is it in? Well, if I use the right-hand rule, this is a minus sign, so that means I'm into the page. So into the page, I'm rotating clockwise then by the right-hand rule. So this tells me my rotation is in that direction, and it has a magnitude of u over h. And so if what I said in class is that the magnitude of the vorticity is 2 times the angular velocity. So this is 2 times the angular velocity, so the angular velocity is u over 2h, and it's clockwise. All right, and again, if I look at my flow, that makes sense. If I put a material element in here, it's going to start to rotate because I have faster velocity on the top than on the bottom. So my element is going to start to rotate. So I guess it's opposite for you. So it's going to start to rotate along these pieces here. So as I'm moving along, a material element's going to be translated in that direction and then rotated as well. Oh, rotated as well. Sorry, I have that backwards on the video because it's projecting onto me. All right, so that's the example I have for kinematics for simple shear flow.